Good afternoon, everybody. So, type 1 and type 2 errors, and how to calculate probability associated with type 1 and type 2 errors. So, if you remember, for type 1 error, we said if H null is true, but we reject H null mistakenly, so basically mu is equal to mu 0, and H alternative is mu is not mu 0. Okay? And if this is true, but we reject H null, which means Z0, which is, write it down here, your test statistic, the absolute value is greater than Z alpha over 2. So in this case, reject H null. So if H null is true, what we rejected, we have type 1 error. And the probability of type 1 error is called alpha. Okay? So what is type 2 error? When H null is not true, but we do not reject it. So in reality, mu is not equal to mu 0, but the test statistic that we have is not in the rejection region. Okay? And the probability associated with that, we call it beta. Then we have 1 minus alpha, which is the confidence. H null is true, and we do not reject it. This is correct decision. It's not error. And the last one is H null is not true, and we reject it. This is called power, or 1 minus beta. Any questions about alpha, beta, 1 minus alpha, 1 minus beta? No questions? Okay. So, and we said how we can geometrically show that what alpha is. So alpha is basically probability of type 1 error or false reject, false alarm, false positive significance level. They're all the same. And it's the probability of test statistics falling in rejection region given the fact that mu is equal to mu 0 or H null is true. So in this case, if I want to show you, mu is equal to mu 0 in this case. As you can see, the distribution mean is exactly mu 0. And if these two are threshold determining the rejection region, this part and this part are associated with alpha. So they are alpha. So half of alpha is here and half of alpha is there. Okay? How about type 2 error or misdetection or false negative? Is the probability of fail to reject H null. In this case, probability of this guy. But we know that H null is not true. So when we say H null is not true, mu is not mu 0 anymore, but mu is something we call, let's say, mu 1. One simple example is mu is equal to 50. So your H alternative is mu is not mu 0, which is not, basically, this is the same as saying it's not 50. So your mu 1 could be any number. Could be 49, could be 51, could be 55. Okay? So let's pick one of those. Let's say 55. Let's say this is 55. Okay? Or 51. Then what is beta? So this is the distribution. And we know that true mean is mu 1, not mu 0 anymore. But some part of distribution is between acceptance region, or it's not in rejection region. What is that part of distribution? Is this left tail. So this is called beta. Okay? That's based on definition. And as we said, beta is a function of how far we are from basically mu 0. Okay? So the difference between mu1 and mu0, beta is a function of that. when we increase basically mu1, what happens? Beta decreases. Okay? Why? Because look at this distribution. When mu1 increases, then the distribution is shifted to the right side. Therefore, your beta is going to get smaller and smaller. Yep.
That's assuming that your mu1 starts above your mu0. If it was below mu0 and you were increasing it.
No, actually, if it is below mu0, then we are talking about decreasing. So it's like the distance, exactly, the distance between mu1 and mu0, which is the absolute value. Yeah. That question? Oh, you had a question. Oh, that was the question.
So I'm having trouble understanding H null being false. So if we say, okay, mu1 is the real mu, and we're guessing mu null, if mu1 is within the 95% confidence of our mu null, does that mean that H null is false, even though they're not the exact same, but still within that?
So the confidence interval you're talking about, so mu naught doesn't have confidence interval. Okay, I mean, so what you are saying is you have a sample, using this sample finding a confidence interval for mu naught. And what you are saying is, now I understand what you're saying. So if your mu0 is here, and if this is the confidence interval for basically upper limit, yes. So this is lower limit, this is upper limit, and based on this confidence interval, if your mu1 is somewhere in between, then you cannot reject it. Then you are doing like beta 1. I'm sorry, the type 2 error. Okay? So if you have some x bar, based on this x bar, you find lower limit and upper limit. Okay?
We're rejecting.
If mu0 is, your mu0 is between L and U, okay, we are basically rejecting that hypothesis test. We are not talking about mu1. Let me explain clearly. So forget about alpha and beta for a moment, okay? So let's say this is your mu equal to mu0 and mu is not mu0. So you get a sample, x bar, okay? And based on that, you find some lower and upper limit, okay? If your mu0 belongs to this lower and upper limit, then you cannot reject H null, okay? Otherwise, you reject H null. So for doing this assessment, we don't have any mu1, okay? So when we are talking about mu1, we are talking about like, okay, if you have this mu1, let's say your mu0 is 50 and mu1 is 51, can you use this procedure to detect this change? Okay? So basically, what it means, the x bar that you are sampling from, the population, actually is 51. Not 50 anymore. So you are basically constructing your confidence interval based on 51, not 50. Okay?
That's why it shifts.
So exactly. So basically, your confidence interval is this confidence interval is for 51 because the reality is 51, and then you compare that confidence interval with mu0. Okay, you got it? Mm-hmm. Okay. Power of test, as I said, is 1 minus beta, and this is very important. Alpha is determined by us. So usually we say alpha is fixed, 0.05, 0.01, any of these numbers. But beta, we need to calculate it. And here is how we calculate beta. Okay? So let's see how we can calculate beta in one simple example. And as I said, beta depends on mu1. Okay? So this is mu is equal to mu 0, mu is not equal to mu 0, or mu is some mu 1, which is mu 0 plus delta. So as you can see, H alternative says mu is not equal to mu 0, which is mu 1, and mu 1 is mu 0 plus delta. So what is delta in this example? Is the difference between mu 0 and mu 1. Does it make sense? Okay? For example, if mu 1 is 51, your delta would be 1. Okay? For the case of mu 0, 50. That's just one simple example. That's to show that how far we are from our mu 0. Okay? Now, let's start with the definition of beta. So probability of test statistic not falling in rejection region. So what is the test statistics here again? Is Z0, and the rejection region is this guy. This is rejection. Remember? So not falling in rejection region is the absolute value is less than this guy. You agree? Given H null is not true, which means your mu is mu 0 plus delta. Okay? Any questions so far? Now let's see how we can solve this. So beta is the probability of, I use the definition of absolute value. So Z0 between the negative and positive number here, given mu 1 is mu 0 plus delta. So what is Z0? Is x bar minus mu 0 divided by this guy. Okay? That's the definition of Z0. Let me just write it down here. So your Z0 is x bar minus mu 0 divided by standard error. So I want to find this probability. Mu 1 is mu 0 plus delta. So what should I do? I want to have x bar in between because I know the distribution of x bar. So therefore, I just do some multiplication and summation to isolate x bar in between. So it's probability of, let's say, mu 0 minus z alpha is, and x bar is in between, mu 0 plus z alpha. This given mu 1 is mu 0 plus delta. Okay? So I want to find this probability. Again, everything else, x bar is random variable, everything else is deterministic, not random variable. That's why I want to have x bar here, because I can calculate the probability easy. So now, what is the distribution of x bar? You tell me. Is normal with what and what? So the variance is sigma squared divided by n. How about mean? Mu 1, mu 0, which one? It's going to be mu 1. Why? Because we said mu is mu 0 plus delta. So H null is not true. So mu is mu 1. So what should I do? I should subtract mu 1 and divide it by standard deviation, okay, to make this standard normal. So I continue here. It's probability of mu 0 minus z alpha, half alpha, times the standard error, minus mu 1. And what is mu 1? Mu 0 plus delta, divided by standard error. So it's x bar minus mu 1 divided by standard error. And that's the same thing with positive sign. Is it clear? Any questions so far? Now it's time for simplification. So we can easily simplify this, going to cancel out these two, cancel out each other, and at the end of the day, I get probability of minus z alpha over 2, and this would be delta square root of n divided by sigma. What is this guy? Z. And z alpha over 2 delta square root of n sigma. So your beta is phi of this guy minus phi of this guy. Okay? So you know delta, you know n, you know sigma, you know z alpha over 2. You can easily find the beta associated with that. And as you can see, beta is a function of your mu1. Why? Because it depends on delta. And delta is basically the element that defines the mu1.
Delta times the rest, like on the left, and then minus something. I guess minus something.
So you mean here, from here to here?
No,
From here?
there we subtracted mu0 plus delta.
Yes.
And on the next line you have it multiplied by delta.
Oh yeah, you're right. Thank you. This is negative. This is negative. Thank you. Just drop the negative sign. It's a huge difference. Okay. So this is the equation for beta. Any questions how we derive that? Good? So here's one example. I'll give you a couple of minutes to find beta for this hypothesis testing. Oh, by the way, before you work on that, so if you have a positive shift, or a negative shift, okay, the beta doesn't change because of the symmetry of normal distribution. Okay, so the direction doesn't really matter. That's why sometimes they define delta as the absolute value of mu1 minus mu0 for two-sided. Okay, so you can define delta as the absolute value of mu1 and mu0 because the direction of change is not important. So this probability and this probability should be the same, but my drawing is very bad, but anyways. These two probabilities should be the same because of the symmetry of normal distribution. Chi-square distribution. T is symmetric, but chi-square distribution is not, F distribution is not, yeah. You need, yes, you need to see, for example, for chi-square distribution is usually say how much sigma has changed, and we don't use like plus delta, we use multiplier for sigma. That's just a convention. So sigma 1 is delta times sigma 0. And delta could be greater than 1 or less than 1. And for greater than 1 and less than 1 are not going to be the same. Any questions? Okay, anybody got any number? What is beta? Nope. Yes.
Standard deviation to the right, and that would affect you by the.
That's one way to do that, but you should know like what
How to
that
actually
means.
work it out.
Yeah, exactly.
Does it mean that it's been reduced by that one standard deviation amount of area, or is it?
It's like this.
More complicated than that.
No, it's exactly the same, but you cannot, unless you know that the probability associated with one standard deviation, you cannot exactly say. So it's 16, and now it's 16.1. Okay, let's say. So what is this probability? Something like that. But we can use the equation as well. So delta is what? Is mu1 minus mu0. So your mu1 is 16.1, your mu0 is 16, so 0.1 is your basically delta, and your sigma is 0.1. Just when you are doing this sort of like, this is not exactly one standard deviation, because the standard deviation of x bar is sigma divided by square root of n. Okay? So that's the difference. So your beta at the end of the day is phi of, what is alpha here? 0.05. So alpha is 0.05, therefore z of 0.025 is 1.96. Phi of 1.96 minus 0.1, your sample size is 9. So square root of 9, sigma is 0.1. Phi of the same thing with negative sign. And this is phi of this guy minus phi of this guy. It's around 14.92%. This is 0, almost 0. And you just find this from the probability, from the standard normal chart is 14.92%. Okay? Any questions? Is it clear? Okay. By the way, so if it is like one-sided, so what you should do is to change. Let me just do that. I think it's not very easy. Let me do the math for one-sided and get the equation. So mu is equal to mu 0. Mu is greater than mu 0, which we call it mu 1. And mu 1 is mu 0 plus delta. So the only difference is in the first part when we are defining the rejection region. Okay? When you are defining rejection region, it's not, this is rejection region. The definition of beta is less than this guy. Okay? So rejection region is Z0 greater than Z alpha over 2. Mu 1 is mu 0 plus delta. Again, what I'm trying to do here is to find beta for one-sided hypothesis testing. I'm sorry, yes, one-sided. This was for two-sided. And if you do that, then probability of x bar minus mu 0 divided by this guy is this. And I guess you can do all the math. At the end of the day, just want to make sure that I'm not making a mistake here. It's positive. Z alpha over 2. I'm sorry, Z alpha. Yeah. You did? I made a mistake here. This is alpha, not alpha over 2. So at the end of the day, this is Z alpha delta square root of n sigma. So this is for two-sided. This is the equation for one-sided. Z alpha over 2 changes to Z alpha. Okay, this is acceptance region. This is rejection region. So we need to find this probability. We follow the same procedure, but at the end of the day, we get this guy. Just make sure that everything is correct. Yeah. Okay. Any questions? Okay. So this is very important. For a given sample size, one risk can be reduced at the expense of increasing the other risk. So what does it mean? It means if n is fixed, when you increase alpha, your beta decreases, and vice versa. Okay? So here is the reason why this is the case. So this is alpha over 2. This is alpha over 2. This is mu 0. Now, let's say, and these are the limits we are using. These are the rejection regions. Okay? So this is lower bound and upper bound of rejection region. Now, let's say mean of process changes to here. And this is mu 1. So what is our beta? Is this side. Okay? Any questions so far? Is it clear? So this is alpha, this is beta. So if I want to decrease alpha, what should I do? Look at L and U. In terms of L and U, we need to widen this distance. Okay? So if you do that, then your alpha decreases. But look at your beta. When you widen distance, beta also increases. So, for example, if I have this guy and this guy. So you can see your alpha decreases, but your beta increases. That's the reason. Okay? So that's why we usually fix alpha. And what we do in order to basically reduce beta, we increase sample size. Okay? So if you fix alpha, then by increasing sample size, you can decrease beta. And here is the reason. This is lower and upper. And let's say this is mu1. This is L and U. This is your beta. So what happens when you increase n? Do you remember the distribution of x bar is normal, in this case mu1, and the variance is sigma squared divided by n. So when you increase n, what happens? Variance decreases. So variance decreases means you have this guy, okay, with the same mu1. So where is beta? It's here. You can see beta decreases. That's the reason. Is it clear? Any questions? Yeah.
The relation with power, so the higher power it's always better to increase the sample size.
Exactly. So beta and power has opposite relationship. When beta decreases, power increases. Okay? So if you increase sample size, your beta decreases, therefore your power increases. Does it make sense? Yes.
If you increase your sample size, can you then also decrease your alpha and maintain your beta?
So you want to have the same beta and then increase sample size. Decrease both of them. By increasing sample size, you can decrease both of them, but yeah, that's possible. That's possible. The thing is, but it's not going to be, the amount of improvement in beta is not going to be the same. You know, for example, if you fix alpha, okay, and let's say you are increasing your sample size by 10%, you gain some power, okay? But if you want to improve both of them at the same time, it's not going to be the same power that you gain. So it's like, where do you want to spend that sample size? Do you want to spend it in alpha or beta? But in practice, we usually set our alpha and then just focus on beta.
The variance has some natural limit, right?
What do you mean by that?
Like, increasing your n, you're going to get diminishing returns on your decreasing variance. Like, there's some true variance, or is it just infinitely decreasable?
So if your n is capital N, okay, so it's very big, okay, let's say if your n increases, let's say 1 million, then your variance is almost 0. We are talking about x bar, not x's, okay, which means that your estimator, your point estimator is precise enough. You don't need any other basically inferences, the confidence interval, because literally your variance, I mean, not literally, but your variance is very close to 0. Okay? Yeah.
Very large samples like millions.
Yep. Because if you have millions,
You are
Okay.
always going to see significant difference.
so yeah, so that's the thing. If you have millions of samples, okay, it depends on your variance. If your sigma is 0.1, like that example before, 0.1, and you have n equal to 1 million, then sigma divided by the square root of n is going to be 0, very small number. So what does it mean? It means that you don't need to do any statistical inference. Just point estimation is fine, because that point estimation is almost mu. Okay? So that x bar that you get using a million sample, you can claim it's mu. And you don't need to do anything else. Okay? Any other questions?
Trying to be confident in your statistical analysis. If you have like a
Based
variance of a
based on the
million.
ratio of your variance and your n.
But
So you
it's-
can see that ratio, whether it goes to 0 or not.
Okay.
Okay? So if it's 0.1, then it goes to 0 faster compared to 1 million, your variance.
Does an order of magnitude greater variance tell you anything of importance with respect to like your sample size? If it's huge compared to...
Yes, if your variance of individual observation is very huge, you need to have more basically sample.
Okay.
Yeah, exactly, because the variance of x bar is also huge. Yeah. Any other questions? You good? Okay. So let's move on to the next one. How we can find sample size? Do you remember we had like a method for finding the sample size for the cases, for basically confidence interval and error of interval estimation or error of estimation. This is a method for finding sample size based on hypothesis testing and your alpha and beta. I go with basically, I start with the second one, which is one-sided, and the first one is very similar. So how we can get that n? We know that beta is phi of z alpha minus this guy. So for one-sided hypothesis testing, which mu is equal to mu 0, and its alternative mu is greater than mu 0. Okay? So this is your beta, okay? And this point here, let's call it A, and this is A. Okay? So if I want to use z function, okay? Z function, I mean z alpha, z beta, z something. To show A, what would be the number for that? Let me give you a little bit hint. Z alpha, z1 minus alpha, z beta, z1 minus beta. Z alpha over 2, no. Z beta over 2. Is it Z alpha? Everybody agrees? Raise your hand. Z alpha. How many? Only 3? 4? 5?
Sorry.
No.
1 minus C alpha
1 minus Z alpha.
is the area, but that value, A, is C alpha.
The value of A is Z alpha. Any other opinion?
Agreeing with that. Yeah.
Are you talking about the area or the point?
I'm talking about A.
Okay.
What A is.
Yeah.
Okay.
A would be
And
A.
that's C alpha.
Is Z alpha. You agree? Everybody? No? Why not? Z beta. So we have another one. Z beta. What else?
It's
What is the definition of Z alpha?
C alpha minus delta root n over
So what is the definition of Z alpha? The point that probability after this point is alpha. Okay? So if I'm looking for something, Z something for this guy, I need to find the probability after this point. So what is the probability after this point? 1 minus beta. So this guy is Z 1 minus beta. Okay? Why? Because probability after this point is 1 minus beta. Probability before this point is beta. You agree? Okay.
The left side.
Yeah, but phi that's the definition of phi function. So that's why beta is phi of some number, okay? Which means the probability before this guy is beta. So probability after this guy is 1 minus beta, okay? So if I want to translate it to Z, it's going to be Z of 1 minus beta. You are right, the normal distribution is always left side, but it doesn't change the definition of Z of something. Z of something, T of something, F of something is always the right side. Make sense? Yep.
So when we had the picture previously of the mu naught distribution with the lower and upper confidence, we had alpha over 2 on the left and alpha over 2 on the right.
Yes.
Does this have any relation to that? Is that line at A also the line at alpha over 2?
So you mean something like that?
Yeah.
If it is Z0, okay, then if alpha over 2 is here, so it's going to be Z alpha over 2. Yeah.
Are those two related? Like, are these two images related, or are they different distributions?
No. This is basically under H null. We are talking about the under H alternative when we have beta. And actually, this is just a simple definition of what Z of something is. That's it. I'm not using any hypothesis testing knowledge here. So what is Z1 minus beta? It's Z of beta, minus Z of beta. This is true also. Why? Let's say if you have any number here, okay, then based on the symmetry, this is if this probability is the same, this is going to be minus Z of something. Okay? So Z of 1 minus beta and minus Z beta is the same. Okay? So then I'm going to combine these two. So my A is minus Z beta. Then I solve it for n. To delta squared? Yeah. That's what I get. So basically what I did, I said given alpha and beta, solve this equation for n, and this is the way I solve the equation for n. Just use the definition of what Z alpha, Z beta is. Okay? For two-sided, yep, go ahead. So delta, so as I said, delta should be given. We say, if you want to detect, so here is kind of problem, or in reality, kind of application of this equation. Let's say your mu 0 is 50, and your mu 1 is 51, okay? So if you want to detect a shift with the magnitude of 1 with the probability of 90%, which means your power is 90%, then what should be my sample size? Okay, so again, with a given alpha, let's say alpha 0.05, okay, if I want to detect a shift with the magnitude of delta with probability of 1 minus beta %, then what sample size should I select? That's the equation for that. Make sense?
This
Okay.
you have Z alpha over 2 plus
Over
Z
2.
beta.
Yes.
So this is the one-sided up here. Is that what you're saying?
This is one-sided, yeah.
Okay.
Yeah, that's one-sided. For two-sided, as you can see, you replace Z alpha with Z alpha over 2, and this is approximation. Okay? And the reason is, here is why we have approximation here. Let's say you have a shift. This is L and U. When you have a change in the mean, your mu1 is, so this is mu0, but your mu1 is somewhere here. Okay? So this is your mu1. So these are rejection regions, and this is acceptance region. Okay? So the rejection region, if your shift is on the right side, so rejection region for one side is much bigger than the other one. Okay? So most of the time, this probability is very small. So we can drop it. When we drop that, when we drop one side, that's why we have this basically closed form solution, and that's why we have approximate. Because if you look at beta for two-sided, you need to solve this equation for n. Okay? And this doesn't have any closed form solution because you have 2 phi. But if you drop 1 phi, let's say, okay, the one which has a less basically probability, then you can solve it for beta. Does it make sense? That's why we have approximate. Phi is a CDF of standard normal distribution. So phi of A gives you this probability. Any other questions? Yeah, go ahead.
That in two-sided hypothesis testing, you need n greater than this value?
Not really, because you are dropping some part of your detection. So your detection power is more than that. Do you know what I mean? Because here is one detection, and the other one is the other detection area. So you are dropping one of them. So it's more kind of like conservative rather than aggressive. So your n should be okay. You don't need to increase that. Yeah. Okay, one example. So it says, so the example we had this before, example 9.2, for mu equal to 50. It says if your sigma is 2, delta is given, and alpha is given. So we want to detect the change with probability of 90%. Okay? I just want to see if it is one-sided or two-sided. Do you remember the original example? I guess the original example was two-sided. Yes. So very quickly, because we are almost out of time. H alternative is mu is not equal to mu0, and mu1 here, actually delta is given, or mu1 is 51. Therefore, your delta is 51 minus 50, which is 1. Your sigma is 2. Your alpha is 0.05. And what you need to do, you want to find n sample size. Okay? If I go back, this is two-sided. I use the approximate equation, which is z alpha over 2 plus z beta squared, sigma squared, delta squared. Detection power it says with probability of 90%. We want to detect that, if you read this. So we want to detect it with a probability of 90%. So our beta is 0.1. So we need to find z of alpha and z of beta. Z alpha over 2 is z of 0.025, which is 1.96. And z of beta is z of 0.1. I don't know what exactly this number is. Let's just leave it as is. And 1 z of 0.025 plus z of 0.1 squared. Sigma is 2. Delta is 1 squared. And then you can get your n. Okay? Any questions? Okay, have a good weekend. I'll see you on Monday.